Logic, biconditionals. Definition. For two statements P and Q, the biconditional of P and Q is the conjunction of the implication P implies Q and its converse Q implies P. The biconditional of P and Q is denoted by the highlighted symbols with the double arrow. So P biconditional Q is the statement P implies Q and Q implies P, the conjunction of the implication and its converse. The biconditional, the symbols highlighted in yellow, is expressed in words as P if and only if Q, or P is necessary and sufficient for Q. Example: if it is raining, I will get wet, and if I get wet, then it is raining. That sentence is the conjunction of an implication and its converse. So it can be written as, it is raining if and only if I am wet. Here's the truth table of the biconditional. Since there's two simple atomics, P and Q, we have 4 rows. We will need P implies Q, and then its converse, Q implies P. We take the conjunction of those two implications, and we have the biconditional. Example: consider the following statements. P, I will pass my final exam. Q, I will study 14 hours. P if and only if Q is, I will pass my final exam if and only if I will study for 14 hours. So P if and only if Q is true if 1. I study for 14 hours and I pass the final exam. 2. I do not study for 14 hours and I do not pass the exam. The biconditional is true when both of its simple statements are true or both of its simple statements are false. Example: for an integer n, consider the two open sentences. P of n, which is quantity n minus 3 squared, equals 0, and Q of n, which is 5n minus 3 equals 0. So P if and only if Q is quantity n minus 3 squared equals 0 if and only if 5n minus 3 equals 0. For what n, if any, is P of n if and only if Q of n true? Solution: consider n equals 3. P of n is true only when n equals 3, because we have 3 minus 3 is 0, squared is 0, and no other n would produce 0. But Q of n is false. So P of 3 is true, Q of 3 is false, P of 3 if and only if Q of 3 is false. Consider n not equal to 3. If n doesn't equal 3, then P of n is false. Q of n is false for every integer, so we have that P of n if and only if Q of n is true for all integers except 3. When both P of n and Q of n are false, P of n if and only if Q of n is true.